Hello, 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 hello.
Okay. 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 Yesterday, we considered this system model and Grand Prix NOMA. So today, we are going to have three more similar scenario. So actually, these four scenarios have been published in last year and this year ICC and Globecom. Last year ICC, last year Globecom, this year ICC, this year Globecom. Journal versions, one published, others are under major revision. So here, so what you have to learn since you are a PhD student. So here, yesterday we considered one model and formulated the problem. So today, three more scenarios. So how to formulate the problem? What is the problem? How to formulate? What are the constraints? Then the solutions. It can be conventional convex optimization solutions. If it is not convex optimization is not possible, so then we go for the machine learning for dynamic optimization. Okay, so here yesterday, so we considered this constraint optimization. So you ask why we can't use the conventional one. Here we are going to have these devices, the number of devices, IoT devices is going to be tens of thousands. So if you take the conventional one, computational complexity increases with the number of this one. So here when we use the machine learning, one agent for each device. So either cooperative or competitive way, they optimize. Say if it is competitive, every device, they want to improve their data rate. So they select two parameters. So the sub-channel as well as the power. These two parameters, they dynamically select. So if it is fully trained, so using the training data set, so then they can make the decision online. So that means they every time slot, they dynamically select the required parameters. So that's what here we are for this machine learning, because when we have thousands of devices, the conventional optimization methods, it takes complexity, very high, time consuming. This one, once you trained it, that's it. So they can quickly select two parameters once it trained. So now, yesterday, after formulated this problem, so here, so we stopped. So what is meant by here? What is meant by optimal solution? So when we have small number of variables, we can do the exhaustive search. So this optimal solution for small number of cases, we got these numbers by exhaustive search. Why? Machine learning, because this is the upper bound. So definitely machine learning will be lower, right? Because it can go to the exact like global search, exhaustive search. It can reach the performance of exhaustive search, no? Because still we have the loss function, no? the loss cannot be zero. So the targeted and the predicted one, there's a difference. The loss cannot be zero. It can reduce it to small value. It cannot be zero. Yeah. 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 So whatever other approximation if you do, you won't get this optimal means for small number of variables. So here we did exhaustive search, and with this blue line, sorry, yellow line, we got by exhaustive search. But yeah, same parameters, yeah. But the thing is, so we haven't done enough training data set. It's not fully trained. So maybe if we have enough data set fully trained, it will reach with a small number of variables. It can reach almost like yellow line. But here we have not trained fully.
By which we got that optimal solution. So obviously that method is better. Why we are going for
This one just to show that for small number of parameters we can get the optimal solution. When we have huge number of devices, we don't know the yellow line. We don't know. We can't do the exhaustive search. Say when you have tens of thousands of devices, so we don't know how could be the yellow line. So in that case, we have to go for the dynamic optimization. This one just to demonstrate with a few parameters. So with a few parameters, so here this one, if you train with more data set, it should go to the yellow line. So now here what we did, so one here two parameters are dynamically selected. One is the sub-channel, other one is the power level. So now if you only select sub-channel, fix the power. So when we fix the power, so say here after certain number of iterations, so the fixed power performance is lower than the dynamic power allocation, because the reason is if it is fixed, so always it gives interference. So if it is dynamic, according to the environment, it can reduce the power. So by that way, the interference can be reduced. But if it is fixed, you cannot reduce it. So that is the reason here. If you don't change the power level, so we won't be. We will get the lower throughput. So that's why to show that okay, only select the channel, not the power. Here yellow one, select both. Power level also is changing and the channel also changing. So now you can see the difference between DQN and double DQN here. So here, as I said earlier, in the DQN that we have the overestimation problem. So overestimation problem is for some actions, they are not optimal action. So, but it gives high Q value. So that is the overestimation problem. So that's what here we use double DQN to solve the overestimation problem. So because of the overestimation problem, so here, the transmit power level for layer 2 and layer 3 same, because it is not optimally selected the power level. So when we have double DQN, it solved the overestimation problem. So here we have separate power levels. this. But earlier when we have DQN, so here the layer 2 and layer 3 use the same power level because they selected the suboptimal overestimation. So that is this is what we use the double Q learning network. So then we did the graph free orthogonal versus non-orthogonal. So if you have orthogonal, so say fixed bandwidth, when you have more IoT devices, so then what we are going to have, we are going to say if it is 10 megahertz, for example, 10 devices we divide by 1 each. If you have 100 devices, we are going to split into 0.1. So then we may not be able to achieve the high throughput because for every device we are going to have very small bandwidth. But here when we use the non-orthogonal multiple access, so we are not going to have the orthogonality. By that way, so here we have the performance gain in terms of throughput significantly higher. Say when you take graph-free NOMA and orthogonal multiple access, so this yellow and this green, the gap. So similarly, the red and the this purple. So we can see so when we take double deep Q network, so significant gain because when we have huge number of devices, when you take orthogonal split, spectrum is split though, so not enough bandwidth. But here non-orthogonal, so by having different power levels, so we can utilize the whole spectrum. Okay, so this is one model that we considered. So here we consider the scenario of, here this one. So here we consider several layers. So then the power level and the sub-channel selection problem. So then we formulated the problem is like this one. So that is we are going to have some rate. So M sub-channels. So for certain time slots, M sub-channel. Each sub-channel we have a number of IoT devices. So we maximize the sum rate subject to these constraints. So this constraint is, so for example, this is one IoT device can occupy only one sub-channel. Here we have the power constraint. So then, so here at a particular channel we have more than 2 devices. Then each channel, so here we have a minimum, each device, it is going to have a minimum rate. So with these constraints, so we use the deep reinforcement learning at the all devices. So they are going to select the parameters to maximize the long-term reward. Yeah. So now this is the first one. Second one, we are going to see, first one is graph-free NOMA. Graph-free NOMA means all devices graph-free. Here semi-graph-free means in practical situations, we have to guarantee quality of service for some devices. So for those devices, we had to use grant-based because we have to make sure quality of service for some devices. So for those devices, we use grant-based. Others, grant-free. So for example, if you take smart meter, so it can be grant-free because it is not urgent. But in some other cases, some other IoT devices, it is essential to maintain the quality of service all the time. So in that case, we are going to have some devices grant based, some devices are grant free. So that's what here in the second model we consider semi grant free NOMA, grant based and grant free. So if you take the scenario, so one resource block, so it's going to be shared by both grant based and grant free users. So here, so the grant based transmission so offers more capacity than needed. So that means so the devices, so the grant based transmission devices, the connectivity, so they have more capacity than the required one. So that is excess capacity they have. So for some grant based devices, the allocated spectrum is more than required one. So sufficient enough. So if they have more capacity so than required one, so then what we can do, that extra capacity we can use the grant free transmission. So say for one grant based one, the required one is say for certain value, but it has excess capacity. So now we can use that the grant free devices, IoT devices, to utilize the extra resources. So here what we are going to do, so here we have millions of IoT devices. So the requirement quality of service heterogeneous, not homogeneous. So then, so in large scale IoT scenario, so this base station cannot control all the devices. So base stations cannot control tens of thousands devices, they cannot control. So in that scenario, how we are going to utilize the resources effectively? So here what we are going to use, we are going to limit the grant free users, the number. Say for example, in one sub channel, so say for example, one sub channel, one grant based user is there. So when we have one grant based user, that grant based user can tolerate certain amount of interference. Beyond that, it can't tolerate. So what base station is going to do, in that sub channel, it is going to calculate what is the interference that grant based user can tolerate. So here what we are going to do, so for each resource block, we are going to have the transmit power pool for each sub channel. So then, like earlier problem, we are going to have distributed power control strategy. So that is the open loop, like previous case. So now the question is, so here, so then after we develop the algorithm, so we are going to compare with semi-grant free NOMA with fixed power control and pure grant free NOMA, and these two schemes we are going to compare. So now, say here we see, say for example, these clusters are sub-channels. Every cluster is like sub-channel. So that is, you have spectrum, for example, say 400 kilohertz, for example. So if you divide into 4 sub-channel, 100, 100, 100, so those clusters are going to select one sub-channel. So now here, you know what is grant free transmission, what is grant based transmission. So now here we are going to have power pool, we are going to have for every cluster. That means for every sub channel we are going to have power pool, we are going to have. So in every sub channel we have grant based as well as grant free users we have. So now the question is, how many grant free users that base station could allow. Because cannot allow, say, arbitrary number randomly, it cannot allow, because it will affect the quality of service of grant based one. So while maintaining the quality of service of the grant based one, remaining you can use for grant free. So now we are going to see how the base station is going to calculate the interference that grant based device could tolerate. So here, if you take the base station, so at a particular sub-channel M, at the base station it is going to receive from grant based as well as grant free. So that I put one cluster, that one sub-channel. So it is going to transmit the signal from grant based device and grant free. So this is the channel gain. So this is the receive signal. So base station, what is going to do? First, base station is going to decode grant based first, because grant based, the priority for grant based, grant free less priority, because the quality of service of grant based should be maintained in certain scenario. So here, decoding order, first grant based, then grant free according to their power level. So this is the decoding order at the base station. So here, again we can calculate the signal to interference noise ratio for grant based and grant free. Grant based signal power, all other grant free users are going to be the interference, then noise power. If you take grant free, the particular device signal power, for grant free we are going to have the remaining devices are going to interfere, because grant based will not come because it's already decoded. So up to J already decoded in the grant free. So for J plus 1 to the remaining is going to be the interference. So now, we are going to have this for grant based, the priority is for grant based. So therefore, for grant based we have the target data rate constraint. The quality of service must be maintained. So that's what, this is the constraint to be met. So first grant based service, quality of service is maintained. So the remaining we are going to use the grant free. So here, base station, what it is going to do? Base station is going to estimate, is going to acquire the channel state information. So for the grant based user, transmit power information, channel state information, everything it will acquire it. Once it acquire it, base station can calculate what is the threshold that particular grant based user can tolerate. So from the grant based user, it can send a pilot symbol. So based on the pilot symbol, base station can estimate the channel of grant based user and what is the transmitted power. So based on that, it can calculate for every sub channel, it can calculate what is the interference threshold. So interference, every channel it can calculate. From every channel, here we assume one grant based. So then what is the interference tolerance for first channel? 5.1, 5.2, all these it calculates. So based on this interference tolerance for each sub channel, the power pool will be decided. Say for example, if the interference it can tolerate is, if it is very low, it can tolerate if it is very low, the power pool power level also below that level. So then the base station broadcast to the sub channel what is the threshold the grant based user can tolerate. So then here we assume that, here we have, this is sub channel 1. in this sub-channel, certain number of grant-based users are going to be there. Certain number of grant-free users are there in sub-channel 1, sub-channel 2, sub-channel 3, up to M. Here we assume that only one grant-based user in each sub-channel. So here, this user, second grant-based user in this channel, first grant-based user in this channel, third grant-based user in this channel. So if you take this channel here, one grant-based and 3 grant-free users. Here one grant-based, 2 grant-free users. Here one grant-based, 2 grant-free users. So basically in every sub-channel we have one grant-based user. Remaining can be 2 or 3 or 4 grant-free users. Depends on the interference tolerance. Say if the interference tolerance is very low, so then the grant-free users can have the high power levels they can have. If the interference threshold is very high, so that means interference threshold is very low, then grant-free users can use high power. If the interference threshold is very small, so that means vice versa, small or high, then vice versa, then the grant-free users can select the power levels.
It's similar to the secondary users in cognitive radio.
Sorry?
Secondary network in cognitive radio. The concept similar.
Yeah, similar to spectrum sharing. So if you take the NOMA principle, like spectrum sharing, so without interfering the primary users, secondary users coexist. But here we have grant-free users and grant-based users like primary user. So now, so here the sub-channel selection. So a particular grant-free user can be only in one sub-channel. So now here the grant-free user is going to select which sub-channel. Then here we are going to have certain power level. So we are going to select one of the power level and one of the sub-channel. So here again, grant-based user, this is the sum rate of grant-based user. So that is in all channels. So we have number of grant-based users. Here we consider one user. So this is the sum rate of all grant-based users. This is the sum rate of all grant-free users. So we have to maximize this sum rate, grant-based and grant-free, where these are the rate of grant free, and this is the rate of grant based. So here the devices have to select the correct channel and correct power level. So this is the problem. Again, we are going to have certain constraint. First constraint, grant based should be decoded first. Then other grant free based on their power level. Then here we have the power constraint for grant free. They cannot have very high power. It will interfere grant based. So then the grant free, they can choose only one channel. So here in a particular channel M, so more than 2 devices, one grant based plus minimum one grant free or more than one grant free. So here we have the grant based rate threshold. Then grant free devices, they must have a certain threshold. So here we have the for M is equal to 1 to M. So this is the number of channels should be less than a certain value here.
One sub-channel, only one grant base can be enough, right?
On one sub-channel, only one grant based here we consider. more than one Grand free. So how many Grand free depends on the interference threshold. Every sub-channel, there's an interference threshold. So every sub-channel,
Observing that threshold.
okay, so every sub-channel, so Grand-based user is going to send the pilot symbol to the base station. Base station estimate the channel state information and the transmitted power. Based on that, it will calculate so how much power needed for the Grand based. So the remaining can be utilized by Grand free. So base station decide the 5.1, 5.2 up to each channel and broadcast. So that means each sub-channel Grand free users can transmit below that threshold. So the power levels are going to be, all power levels are going to be below that one. So now, okay, so these are the constraints. So now here we are going to have competitive deep reinforcement learning. So one is cooperative, other one competitive. Cooperative means, so that means all users have to achieve, then only the reward will be given. If it is competitive, so they are greedy. So that means every device, they want to achieve their rate. So it does not care about the other one. So that is here. So every agent, so here the reward will be given for the agent. So if the agent select one sub-channel and one power level, when it select these two, if the rate of that particular device at the next time slot is greater than current time slot, reward is given. So here you have 10 devices. Second device, pick up one channel and one power level and calculate its rate. It is better than the previous time interval, so reward is given. Because this is competitive, it doesn't matter but how about the performance of other devices. So now this is how the reward is given. If it is not, reward is zero, no reward. So here we are going to have another version of deep Q network. Earlier we learned double DQN. Now here we are going to have another DQN that is called dueling DQN. What is dueling DQN is? So here, so this is the Q value is going to be split into two. What is advantage function and value function. So why this Q value is split into this is because some states and some actions are not significant. So those states, because we are going to have thousands of hundreds or thousands of states we are going to have. So if you consider all possible states, from that state all possible actions, to converge it will take long time. To solve that problem, so here the double deep Q neural network so is going to identify best action and important states. That is the purpose of dueling. So here earlier we learned what is meant by double DQN. So decouple the selection and evaluation we learned earlier. So now the split the Q value calculation into two. One is advantage function, other one is value function. So that means if the particular action gives minor increment, so those kind of irrelevant actions, irrelevant states are discarded. Only selecting the best action and best states, by that way it can converge faster. So that is the purpose of this dueling. So here when you have dueling, we can see the without dueling, so double DQN, without dueling and with dueling. So here with dueling, it converges quickly above. Without dueling, it is going to go all states, all actions. So even not significant state and not significant actions. So that's what to converge it takes long time, because you can see agents learn and refine their policy faster. So after 100 episode here. So then without dueling, it learns slowly and converge after 220 episode, because this dueling identify the best action and important state. So that is the to converge faster, this dueling operation is done in the DQN. So earlier we learned why we have double DQN to avoid the overestimation problem. Now why we have dueling is so to avoid insignificant state and insignificant actions. So here again we can see, so here the learning and convergence analysis. So for small set of state, both are almost same. Say if you have the number of devices only few, so no need to ignore the insignificant state or insignificant actions. But when you have huge number of devices, huge number of states, huge number of possible actions are there, then only we have to use the dueling. So when you have small set of data and actions, so both performance almost same, because we don't need to discard. So now, so the impact of power levels. So here we have the power levels, so 1, 3, 9, 7, 5 like this. So when we have small number of power levels, so it converges quickly, but the problem is low throughput here, because we cannot control the interference. When you have more power levels, by selecting suitable power levels, we can reduce the interference effect, so we can increase the throughput here. So here when we have 5, so in terms of convergence, we have to balance the trade-off. So that means throughput and convergence. So power level, say not too high, 7 or 9, or too low, 1 or 3. In between is the best trade-off in terms of throughput as well as convergence. Now we can see, so here number of grant-free users. So it is obvious that when you increase the number of grant-free users in one sub-channel, performance of grant-based will decrease. It is obvious. So you can see, so the grant-based is the yellow one. So when the number of grant-free users increases, so the yellow one decreases, because when the number of grant-free users increases, so interference will increase. So therefore, the performance of grant-based will decrease. It's fine. But when we have the throughput, because some throughut for grant-based, grant-free will increase, because we are going to have more grant-free users. So when we take the distributed power control and fixed power control, so distributed power control, since we have multiple power levels, the throughput of both grant-based and grant-free better than fixed power control, because when you have fixed power, you cannot control the interference. So here, so the throughput of grant-free increases. So that means, so we are going to effectively allocate the redundant resource of grant-based user. So that means grant-based user has excess resources. So that excess resources we utilize by having grant-free users. Again, now we see, say here, so we scalability. So here we change the number of devices from 9 to 30. So IoT devices 9 to 30. So when you have the IoT devices from 9 to 30, so in terms of convergence, so almost same. So therefore, so this scheme is computationally scalable. So that's what here this is advantage over the conventional optimization, because this is scalable, because each device compete each other. So when the number of devices increases, it will not affect the computational complexity. So that's what here the advantage over the conventional optimization. If you take conventional optimization, the complexity will increase with the number of devices. So here we see the number of grant-free users in each cluster or sub-channel. So we consider the number of grant-based, grant-free users in each sub-channel. So when we have 4 grant-free users, so here we get the throughput high, because if you increase the grant-free users further, it will affect the grant-based user. So then we cannot increase the grant-free users too high. At the same time, we can't reduce the grant-free users too low, because to have the sum throughput of both. So here in this, the numerical values, we found that the grant-free users not too high, not too low. So in between, so we get the sum rate higher compared to the other numbers. So then, so here we see the dueling based one, so achieve around 22% than the pure grant free normal, no grant based, just only have grant free. So here more throughput, because here we guarantee the throughput of grant based. So here we have the total throughput, grant based and grant free. So instead of having only grant free, by having grant based and the remaining excess resources we utilize for grant free, so then we can improve the overall throughput here. So here then we consider the fixed power control. So when we have fixed power control, the performance is around 17.5% better. So from these two, what we found that with the dueling operation, what we found that, so if we have semi-grant free with the distributed power control, we can improve the throughput, because basically the idea is, so for grant based only scheme, we allocate excess resources. That excess resources we can utilize by finding the interference threshold, so without affecting the quality of service, the remaining power could be utilized by the grant free users. Then again, here we found the power pool associated with each sub channel. So sub channel 1, these are the power levels. Sub channel 2, 3, and different power levels. So each power pool is mapped to each sub-channel. So actually base station, when it broadcasts the interference threshold, it will broadcast every sub-channel, these power pools also. So here we have open loop power control, not closed loop. So here, so say here the proposed one, because if you take the conventional one, we use the same power level. So here we have different power level. So because of that, the performance is better than the conventional open loop power control, means fixed power level for all users, not variable, so not dynamically selecting the power level. So here the each users can select the best power level according to the channel gain and geographic location. So by that way, we can improve the performance compared to the fixed power control. So this is the second scenario that we considered. So first scenario, only grant free. Second scenario, semi grant free. Now the question is, the third scenario, the question is, sometimes two devices, two grant free devices select the same power level. Sometimes say for example, so in one sub channel, three power levels are allocated. So when three power levels are there, so when the users select a power level, two users select the same power level. Say in power level you have P1, P2, P3. User 2 and user 3 both select the power level P2 from the power pool. So when they select the power level, so they select according to the reward function. So two users select the same power level such that, because here competitive, such that I can improve my throughput. Other one also select that one, that power level, I can improve the throughput. So that means two users select the same power level to get the reward. So in that scenario, how we are going to have, we cannot decode. Because if two users select the same power level, because successive interference cancellation cannot be done. So then what will happen? Collision occur. So in that case, how we are going to solve the problem? So that is the one next problem that we are going to consider. So here, how to mitigate the transmit power collision? How we are going to not here, no, come here. Sorry. Okay. Okay, same frequency. One grant based, say 2 or 3 or certain number of grant free.
Here basically we are watching
The grant free, they are going to select one of the power level from the power pool. So
our throughput. We follow the sum rate of grant based as well as
yeah,
both methodology with all if we are doing what have been compared with the machine learning technique.
yeah.
Giving some throughput 2%. It is again the same overall the throughput results. So how means done, what work have been done that it is something
Why these ML techniques are performing differently?
not means
Why?
techniques.
All are machine learning techniques, but what is the reason they are performing differently?
What parameter has been taken and on what parameter I have means on what parameter the work has been done that it is giving me.
This one.
It is the throughput means data rate.
Yeah. So here two different scenario. One is fixed power. The one that we are considering is the different power level.
Is suppose grant based user in that sub channel power allocated power something P1 the grant P have been allocated power P2 and P3. Now we have applied one methodology and now we have calculated number of equals. Now we again work with other methodology get the throughput of all the three dots.
So here the grant free users every time slot are taking different power levels according to the channel conditions. Yeah, but if you take fixed power, whether the channel is changing or not, the power is fixed, not changing, they're not dynamically changing. Not grant based, the fixed power control. Here I am comparing with fixed power control here, 17.5% means. So for grant free and grant based, the power allocated is fixed, not changing with the channel conditions.
That is the different thing that we upon the channel gain we decide how much power should be.
No, fixed power allocation is every user, the power is allocated fixed. So that means whether the channel is changing or not, the power allocation is fixed. Here, power allocation varying from the power pool, it select one of the power according to the channel condition.
Which means not equal. One is given to you, so whatever the condition of channel are there, you will take T1 only. Right? But if it is dynamic, you can
Say one grant for a user, say if it is power 0.8, so always power 0.8, no changing. But here, the depends on the channel condition, not 0.8, it can be 0.4, 0.6, 0.7. So like this, according to the channel conditions, from the power pool, it varies. So by varying, we can reduce the interference for the grant-based user. We can reduce the interference for the grant-based user. If you fix it, so sometimes you are going to interfere grant-based user. Because your power is high, it is going to affect the grant-based.
Grant-based is higher.
Yeah, power of grant-based is higher, is fine. For grant-free, so even if you allocate high grant-based power, if the channel condition, channel gain worse channel, so what is the receive power by the grant base from the grant base is going to be very low, no?
But that's why that channel gain is not from the and the grant free power will actually
If the grant based, if you give 1 watt, so at the base station is going to receive, depends on the channel condition. If the channel is good, say it receive 0.9. If the channel is bad, so it will receive 0.6. In the grant free, if you have fixed to 0.6, this one is going to interfere. If it not fixed, then according to the channel condition, so what will happen? This one will reduce to 0.2 grant free.
now how this scenario is
discuss later. We will discuss offline.
Okay.
Very good.
Okay. So now we are going to when is the break? Still we have time. Okay. So now how we are going to mitigate the collision. So here, so here the non-orthogonal multiple access, so largely depends on the channel gain. So here the normal scenario, so non-orthogonal multiple access, so needs perfect channel state information. Then only it can decode. So now, so if you, for all devices, if you are going to have channel state information, perfect channel state information, at the base station, the computational cost at the base station is going to be very high. So that's what here we have this random access grant free transmission for short packet IoT devices like we did earlier. So we are going to have a power pool for the grant free users that we did earlier. So now the question is, so the main problem here is whether it is grant free or semi grant free. So how we are going to mitigate the power collision? So that means, so more than 2 users, for example, so or more than 2 users select the same power level. So what does that mean? What does that mean? It's like this here. So here in a particular sub-channel, so you have these 4 power levels. So 2 grant free users select power level 4. So 2 users select 4. Then what will happen? We cannot decode. So in the same sub-channel means their channel gain nearly same. So then what going to happen? So collision will occur. So in this case, so all 4 users select 4 different power levels. Here in this channel, no collision. So if collision occur, how we are going to?
Distance from the base station.
Sorry?
The distance from the base station will also matter.
Yeah, distance also matter. So here we have the same cluster, one sub channel for same cluster. So the devices are almost in close proximity. So now the question here is, so how we are going to solve the power collision problem? So then another problem is, so that means here more than one device, so they select the same power level. So now we are going to see in the machine learning, the fast convergence and slow convergence. So how we can achieve a fast convergence at the same time? So how we can avoid the non-optimal solution problem also, how we are going to achieve. So that means the difference between competitive and cooperative. So the devices, so if they compete, what will happen? If they collaborate, what will happen? So 2 types of the multi-agent deep reinforcement learnings are there. One is competitive, other one cooperative. So now, so the cooperative and competitive, they have different advantage and disadvantage. We are going to see. So whether we are going to use competitive or cooperative. In the previous work, we used the competitive. So that means each device improve their rate, doesn't care about the other devices. Now we are going to see, so we are going to propose a hybrid scheme. Hybrid scheme means cooperative and competitive. So certain percentage of time it will cooperate, certain percentage of time competitive, because cooperative and competitive, they have separate advantage. So to achieve the advantage of cooperative, to achieve the advantage of competitive, we are going to have hybrid scheme, cooperative and competitive. So now we see how we are going to see the hybrid scheme. So see what is meant by, first we see what is meant by cooperative and competitive. Here, this is an example. What is meant by competitive? Say here, you have 4 users. When you have 4 users, user 1 and user 4 select the same power level, P2. So then for them, in the case of competitive, reward for each device, irrespective of other device. So therefore, for these two, the reward is 1. For this one, reward is 0. So this is competitive. If it is cooperative, so here, so these two selected different power level. These two selected the same power level, but reward for everybody 0. Because cooperative means everyone should succeed, not single one. But if it is competitive, irrespective of the other device, if I succeed, I will get the award. But if it is cooperate, now 4 people play the game. So if all 4 win, only reward. If 2 win, 2 lost, no reward for anybody if it is cooperative. If it is competitive, if 2 win, award for those 2, others no award. So that is the difference between cooperative and competitive. Hybrid means like this. So here they get the same power. So for reward for them it is 0. For this one, earlier if it is competitive, reward 1. Cooperative, reward 0. In hybrid, based on a threshold, we are going to give the reward 1 or 0. Earlier, either 1 or 0. If it is competitive, is 1. Cooperative, 0. Now we are going to have a threshold. Based on that threshold, it can be 1 or 0. So that is the hybrid. So why we are going to have hybrid is because in terms of convergence, the competitive and cooperative different performance wise. So in terms of the final reward performance also they differ. So by having appropriate threshold, we can achieve the benefit of both cooperative and competitive. So here in this power selection, so here the power collision problem, we are going to have hybrid scheme. Okay, so now we are going to consider the scenario here. So here, so every sub-channel we consider as a cluster. So for every cluster, we are going to have a separate power pool. Power pool 1, power pool 2, power pool 3. So here, base station is going to broadcast the power level. So as I mentioned earlier, base station, it calculates the interference threshold. If it calculates the interference threshold, according to that interference threshold, it is going to design the power pool and broadcast. So now we are going to have like earlier, so each power pool is going to have certain number of power levels and it supports certain number of grant-free users. So here we have some binary variables. So a particular user, if it selects a particular power pool, then we say that constant is 1, otherwise 0. Similarly, certain power level, if it select, then we consider that variable x either 1 or 0, depends whether it select a certain power level. So now here we have another variable. So here, so if a signal for a particular user decoded successfully, we take that variable as 1. If it is not successfully decoded, -1. If the signal is not transmitted, if it is 0. So here we have few variables, takes the binary value 1, 0. So that means one binary variable. So if a particular user selected a particular power pole, other one, if a particular user selected a particular power level. So by this definition, we are going to see the scenario when the collision will occur. Okay, so now how we are going to formulate the performance metric. So here the problem is avoiding the collision, not the sum throughput here. Here, how we can avoid the collision. So the metric will be different. So here, so if a particular user, user N in a particular sub-channel, if it decoded perfectly, so then we are going to have the value R1, otherwise value 0. So that means if two users select the same power level, they cannot be decoded. So then the value will be 0. So here if they decoded correctly, the value is 1, otherwise 0. So that means this value can be 1 or 0. In a particular user, particular channel, if they decoded correct, then this is 1, otherwise 0. So now we have total grant-free number of users. So here we have number of sub-channels. So here certain time slot, and we take an average. So here this is the metric. So now we have to maximize this metric, because if we have to maximize the number of users successfully decoded, no collision. We have to, if we avoid the collision, they can be decoded. So now with this we are going to have, so now the problem is to maximize this. If you maximize, so that means we are going to maximize the number of devices successfully decoded. So now, so again the constraint, so we are going to decode according to the power level. Then here these constraints are, so that is one particular user can select one power pool and one power level. Then this is the constraint for grant-based user should meet the threshold rate. These are the power constraint. Then this one, the number of power levels greater than number of devices. So now, G, which one? 22? This one. So the decoding is in the high power first, then that is a normal principle. So here the one user select only one power pole. The next one user can select only one power level. Because W and X, here I defined here. W is 1 if the user selected power pole, that particular power pole. So X, a user selected a particular power level. So here we have different power pool. Every sub channel we have one power pool, because in that sub channel power pool decided by the interference tolerance of grant based user. The power pool decided by interference tolerance in that channel. For grant based user we give the priority. So he can tolerate this amount of interference. According to that, the power levels are decided.
More than half of the power.
For grant based user,
Half of the power should be.
it depends on the channel content. If the channel is very worse, then more power should be given. Then only the grant based user can meet the threshold rate. Yeah, because if the channel is very worse, so the grant based user has to use high power, then only at the receiver it can meet the threshold rate. This rate here. Say this rate can be achieved if this SINR meets certain value. If the channel is very poor, then SINR is very low, it can meet that constraint. Yeah, for grant free users. So this one calculate, so how much power could be used by the grant free users, because this one has to meet this threshold. To meet this threshold, it must have certain signal to interference noise ratio. Say this is a threshold here. Based on this threshold, you can calculate what is this value. If you know what is this value, then you know what is signal to interference noise ratio. From that, you can find what is the interference that it could tolerate. The grant based can tolerate this amount of interference. So, based on that tolerance, grant free users can select their power within that tolerance level. Base station, calculate. Grant free. Okay, so now we are going to see the algorithm whether it could be fully cooperative or fully competitive or mixed. So here we have the power pool and power selection problem we can formulate as a Markov decision process. Here the agents are going to be the grant free users. Every grant free user will be an agent. So here the state in a particular time slot ST, so it includes the decoded status, selected power level and power pool of the users. So here we define the state. So the local state for an agent at a time agent N. So that agent now in which state? Now selected with power pool, which the device selected with what power level, and this is the status, decoding status, whether it's decoded or not. So that is the agent now is in current what state. So that particular device now at the moment which power pool is selected, that device which power level selected, now whether it decoded successfully or not, that is the current status. Now it is going to move to the next state. So next state which power level it's going to select, then whether it decoded correctly. So by the particular action. So here, so the action, so the selection of power pool and selection of power level. So here action 1 is the power pool selection part. This is the power level selection part. So action here, 1 selection of power pool, action 2 selection of power level. So that is going to be the action. So you know what is state? State of the agent is here. This is the state of the agent. This is the action of the agent. Now, when an agent select an action, so he is going to get the reward. So here, so the agent can select this power pool, or this power pool, or this power pool, or this power pool. Then, if it select this power pool, then one of this power level it can select. So agent. So agent, so for example here, agent is one device. It is going to select one of the power pool. If selected that particular power pool, it is going to select one of the power level. Now, so we are going to see the reward. So we know what is the state and what is the action. Now what is the reward? Reward is 1 or 0 for the agent. When he selects a particular power pool and power level, the action 1, if no power collision occur and successful decoding, then reward will be given. If the agent select with another agent also same power, collision will occur, so no reward. So reward can be 1 or 0 for the agent for the action he is going to take. So then it will go to the next state. So now, as I mentioned earlier, so you know what is meant by competitive. So then you know what is meant by cooperative. Then you know what is meant by hybrid. So here, to avoid the disadvantages of competitive and cooperative, so we combine the advantages of these two algorithms. So agents behave cooperatively or competitively based on the threshold draw, the hybrid one. So now we are going to take the scenario. So network-based scenario. Network-based scenario means we don't have cluster. So all devices distributed everywhere. So at the network level. So here cluster level is this one. So in the cluster level, they are going to compete at the cluster level. So one agent will not compete with the other cluster. They compete within the cluster. If it is a network level, all compete each other. If it is in the cluster level, so they are going to compete or cooperate within the cluster level. So within themselves they cooperate, or within themselves they compete. That is the cluster level, competition or cooperation. So now clustering, so this is like unsupervised learning. So unsupervised learning, so you know the k-mean clustering based on the distance. So we can group the devices, different clusters. Then for each cluster, we can assign a power pool. So clustering based on the user locations or distance. So nearest users form one cluster. So now, so here, so we are going to use the non-orthogonal multiple access for the cluster. So now we are going to see, so learning stability and convergence. Now we are going to see how, with the number of episodes, how the reward varies for all three schemes. If you see here, so the convergence, if you see the blue one, hybrid one, the converge just quickly. But if you take the cooperative one, so it takes long time to converge, because you know why? Because if it is cooperative, if two devices, as I said earlier, they won't get reward. So it will take long time to converge. At the same time, their reward final after convergence, the final reward is lower than the competitive or hybrid one. So when you take the competitive one, so here this one, so initially they converge little faster, then later it converges slowly. So here, if you see the behavior of competitive and cooperative, so we have competitive one. So the initially here it moves faster, but the final reward is lower than the cooperative or hybrid. So the cooperative, so initially convergence slow, but in long term it reaches the reward like hybrid. So if you take the convergence, so cooperative is slow. So the hybrid achieve the better performance compared to competitive alone or cooperative alone, because it takes the benefit of both. So here we considered the trained agents at different locations. So we found similar results for when we place the agents at different locations. So that means the convergence behavior, so when we do at different locations, it gives similar results. So here, if you take the agents behavior, so now we are going to see competitive cooperative and cooperative competitive scheme. So that means initial 50% of the time the competitive, then the last rest 50% of the time collaborative, then vice versa. So 50-50, but first competitive, then cooperative, or first cooperative, then competitive. So here, so when we see this one, blue, so first competitive, then cooperative. This one is first cooperative, then competitive. So if you take the competitive first and cooperative, so performs better than the other one. So to find the optimal solutions, they compete first to get the reward, then after they collaborate. So when you take the collaboration first here, so then that means when all devices succeeded, only they will get the reward. So that's what here initially they won't get any reward, because to get the reward all should succeed. So that's what initially no reward, very low reward here, but after some time their reward moves up. So this is the observation whether first competitive or first cooperative. When you have first cooperative, it will take long time to get the reward, because if one failed, all get reward 0. So then we did the what is meant by optimal solution is here we have number of devices 12. So optimal means maximum 12 could be saved, could be served. So that means the 12 is the number of devices here we have. So the optimal solution is 12. So 12 devices. So optimal maximum number is 12. So here when we take the hybrid approach and cooperative and competitive approach, so the hybrid one, the competitive one and the cooperative one all reach the final same reward, but the convergence the quickly for the this hybrid one converges first after 200 after nearly 300 episode. So if you take the random selection, so this is the randomly select. So the average successful decoded users very low. Okay, so what's the time now? Okay, we can have break 10-15 minutes.
Like to see you.
Yeah.
Some tattoo stuff, something.